All right, now on to some brainless slides. These are pretty rose curves. Polar graphs make some pretty neat shapes. Rose curves just look like flowers. They have different numbers of petals depending on their numbers inside the arguments. There are curves in the limacone family. You can see that some limacones are dimpled, some have loops. There's a cardioid, which is what our last shape was, that kind of looks like a heart. Some kids say it looks like a butt. Honestly, I really can't argue that, I guess. But it's a cardioid. It's meant to look like a heart. You have lemniscates, which look like figure eights. Ooh, that kind of rhymes. And then there's the spiral of Archimedes. And the equation of that actually is kind of cool. It's R equals theta. If you ever want to put that in your graphing calculator and just watch it whirl around, it'll make you dizzy. It's like one of those optical illusion things when you spin the wheel. So anyway, you do not have to memorize those. I just wanted to let you hear the pronunciation of some of those in case the book mentions a lemniscate or a cardioid or a limacone. You'll know what it is. You can refer back. Okay, now this is the part of polar functions that will be the most appropriate for the College Board exam. They're always going to ask you a question about finding a polar area. To do this, we need a formula, and we're going to derive it right now. As we've known for a long time, the area of an entire circle is pi r squared. But if you just take the yellow sector only, it's 1/2 theta r squared. And I'm asking you, why is that true? Well, here's the reason. Again, we know that the area is going to be pi r squared for the entire circle. But let's say that this angle here, theta, was 45 degrees. Well, then it would only be 1/8 of the circle, and 1/8 is 45 3/60ths. Or let's say that theta was 90 degrees. That'd be 1/4 of the circle, or 90 3/60ths. Well, it's theta degrees, so that's theta 3/60ths, except that we're in radians, so instead of saying theta over 360, we say theta over 2 pi. That's the radian equivalent. At this point, you can think of a 1 being here. The pi's are going to cancel, and there's your formula, 1/2 theta times radius squared. Therefore, it would follow that the area of any polar region, from theta equals A to theta equals B, would be 1/2 radius squared d theta. Again, you're going to integrate it, so you're going to go up by a power of theta to get that theta into the formula. So this is the formula that you absolutely, positively need to know. Polar area, 1/2 integral radius squared. All right, let's try to find a few polar areas. Number 6, find the area of one petal of this rose curve, r equals 3 cos 3 theta. Okay, here's my plan. I'm just going to find the pink area, and then I will double it to get the area of a full petal. Right now the pink is half of a petal. The reason why I'm going this route is because I realize that theta equals 0 is out here. If I make theta equal to 0, I get 3 cosine of 0, which of course is 1, and so the radius becomes 3, which is exactly where my green dot is. If theta is pi over 6, and the pi over 6 is put in, I get 3 cosine of pi over 2, and of course cosine of pi over 2 is 0. That shrinks the radius down to 0 and puts me at the origin. So I realize that my area I can attain if I just go from 0 to pi over 6. Now again, normally the formula for polar area is 1/2 integral of radius squared d theta. However, I need to double my answer because I only colored in half of a petal, so I have to multiply by 2, which just sort of conveniently is going to cancel the 1/2 out. Okay, again, this is radius squared, so we're going to dump the radius in here. In simplifying the integrand, you're going to have the integral from 0 to pi over 6 of 9 cosine squared 3 theta d theta. Of course, I just pulled the 9 out because I can. Let's see, cosine squared. Remember that is the memorized formula that we learned. Sine squared and cosine squared, when you integrate it, the only way to do that by hand is to take a half angle formula from the golden sheet. I don't think we want to do that right now, so let's just go with what we know. The 9 is out front. The integral of cosine squared of something is always, always, always 1/2 theta. Cos is the plus. Normally it'd be 1/4, but with this 3 being the coefficient, it's going to be 1/12. And then you double the angle with the sine. It's always sine. So sine of 6 theta, not 3 theta. And we're going to evaluate that from 0 to pi over 6. Okay, let's try it. Starting with the 9. In with the pi over 6. Half of pi over 6, of course, is pi over 12. When you put the pi over 6 here, you get sine of pi, which is 0. Putting the zeros in will give you a pair of zeros as well. So it's simply going to be 9 pi over 12, and 9 pi over 12 will reduce to 3 pi over 4, and that will be the area of the full rose petal. Number 7 wants us to find the area of the interior of this shape. 4 plus 2 cos theta will be the radius. Again, I want to figure out what our limits are here. A lot of times you'll have a graphing calculator on these and you can trace. And if you have that capability, you should. If you don't, we'll realize that theta equals 0 sits right here on the x-axis, as it so often does. If you're not sure, try the 0 in here. Again, cosine of 0 is 1. This would be 4 plus 2 times 1, that's 6. You can see that that works. So yeah, that is where theta equals 0. And then over here, theta is going to be pi. We can verify that as well because the cosine of pi would be -1. So you'd have 4 minus 2. It would still be 2, and the radius is 2 right there, as you can see. So if we go from 0 to pi, we'll get the top half of the shape, and then we'll just double our answer. Or if you prefer, you could go from 0 all the way to 2 pi. That'll take you all the way around. I think I'm going to go from 0 to pi and double my answer. Again, the 2 and the 1/2 are going to cancel out. I will have to take this and FOIL it out if I do not have a calculator. If I do have a calculator, I'm plugging it in right away and getting my answer of 18 pi square units. There's no reason to be a hero if you have a calculator section. You plug that in. All right, let's get 18 pi square units the non-calculator way, just to make sure that we're covered in all scenarios. Okay, I FOILed it out. At this time, I could decide to factor out a 4. I think I'm just going to leave it in, but certainly you can factor that out. In fact, that might be smarter, but I'm just going to forge ahead and integrate term by term. Okay, putting in the pi, we're going to have 16 pi plus 16 sine of pi, which is 0. Putting the pi in here, you're going to have 1/2 pi, but you're multiplying by 4, so that's 2 pi. Sine of 2 pi, of course, is 0. That wipes the rest of it out. And plugging a 0 into the entire thing is going to give you a 0. And sure enough, guess what? We got the correct answer of 18 pi square units for the area of the interior. Number 8, we want to know what's the area of the inner loop of that shape, r equals 2 sine theta minus 1. Well, the first thing I want to do is see where this graph starts at. Again, my graphing calculator is a great source, but assuming I don't have it, let's make theta 0, which would actually make the radius -1 and put me right here. So that's a little bit odd. By the way, that's also theta equals 2 pi. If you were to put a 2 pi in, you get the exact same result. You'd be at that red point. Well, we want to know, where does this loop start? In other words, where is this green point? Where do we get to that the first time? Well, at the green point, I know that the radius itself is 0 because you're at the origin. By setting the radius equal to 0, you can see that sine of theta would have to be 1/2. And that would occur in two places. Either theta is pi over 6 in quadrant 1, or theta is 5 pi over 6, and that's in quadrant 2. Finally, I'm interested in knowing where these points are, this blue point and this purple point. I have a gut feeling that the blue point might be theta is pi over 2, and I would be correct. Let me show you why. If you take the pi over 2 and put it back in your original equation, you get this. Sine of pi over 2, or the sine of 90 is 1. So you have 2 times 1, 2 minus 1 is 1, and the radius up to the blue is 1 unit, so that does make sense. The purple, I have a feeling might be 3 pi over 2, and it will be. Again, you can see that the sine of 3 pi over 2, or the sine of 270, is -1. So you have -2 minus 1. The radius is -3. But keep in mind, though, that you're in polar coordinates, and 270 degrees is all the way down here, but instead of the radius being 3, it's -3, which means it goes up 3 spaces and puts you right here where you would expect. So I've got all basically the border points labeled, so that way I can figure out what are my limits of integration, and I can go from there. If I was to have the calculator trace this curve, or if I was to do it myself, I would obviously start at theta equals 0, which is here. I don't want this part, but as soon as I hit pi over 6, it's on. And when I get to 5 pi over 6, I stop. Again, I don't need to continue on. If I go from pi over 6 to 5 pi over 6, that'll give me the area of the inner loop, which is what I wanted. So that's going to be my game plan. We're going to integrate from pi over 6 to 5 pi over 6. If I prefer, I can simply integrate from pi over 6 to pi over 2 and then double my answer. I think I'm just going to go ahead and plow straight through to 5 pi over 6. Again, there's some flexibility here. Now, of course, if you're allowed to plug this into your calculator, I want you to take full advantage of that. If in the event you do not have a calculator, that's fine. We have to square it out and then integrate it by hand. So that's what I'm going to do now. Okay, there's the FOIL. If you simplify the inside, you're going to have 2 theta minus sine 2 theta plus 4 cos theta plus another theta. So that's actually 3 theta minus sine 2 theta plus 4 cos theta. I'm clearly running out of room, so I'll take this to another screen and we'll finish up the plugins. Okay, plugging the 5 pi over 6 into all parts is going to give us this. And plugging the pi over 6 in is going to give us this. I went ahead and made the trig substitutions back in. And to be honest, College Board will never make you do anything this insane. This is pretty crazy. There are some things you can combine. For example, I see 5 pi over 2. You're going to take away a pi over 2. That'll be 4 pi over 2, which is just 2 pi. Again, you still have your 1/2 in front. So those are out. You've got a positive rad 3 over 2. You have another positive rad 3 over 2. That's going to be rad 3. The 4 and the 2 will cancel. So this is going to be -2 rad 3. This negative is going to come here, again canceling. Another -2 rad 3. There's a 1 on that. Putting this all together, you're going to have -3 rad 3. And so your final answer will be 1/2 times 2 pi minus 3 rad 3. And that will be the area of the inner loop. Okay, number 9 wants the area between the loops. And so to do this, you're going to find the area of the outer loop and subtract the area of the inner loop. But when I say area of the outer loop, I'm talking about the area of the entire thing that's yellow right now. Okay, I set the radius equal to 0 just to see where we were in terms of angles. And if the radius is 0, then theta will be either negative pi over 6, 7 pi over 6, or 11 pi over 6. I'm going to take those numbers and put them into the limits of integration, and then I will explain to you why I did what I did. Okay, just humor me for a second. Let me tell you a story. Let's pretend that you're standing at the origin with a water gun, and there's a line of people all the way along the shape, and you start spraying them. You're nailing them with this water gun. It's like a high-pressure water gun, and they're just getting pelted with a stream of water. And I started straight to the right because that's where theta is 0. And I'm hitting people. And this is awesome. It's almost like I'm painting a picture with streams of water. And I get all the way up. It looks like I'm making some sort of a seashell here. I get straight up to pi over 2. And I keep going. Till I get all the way to here, which is pi. And then I continue going until I'm down here at 7 pi over 6. What happens at 7 pi over 6 is these people, I'll make them different dots here. These people over here who are red basically get sick and tired of being pelted by this water gun. And so they decide they're going to charge in and attack me. And here's what it looks like as a close-up if I was to zoom in on quadrant 4. Again, I'm spraying the water gun. I get past pi or 180. And finally, these people are like, we're not taking this anymore. And they start to charge in at me, even though they're taking a hit from the water gun at close range, and they tackle me. And at that point, the radius is 0, which we've already discovered occurs at 7 pi over 6. So again, that's why I put that in there. Now let me back up a little bit. You can see that I have sprayed this entire region blue except for this little bit in quadrant 4 that I haven't touched. I have to back it up a little bit, and that's why this water gun didn't actually start at 0 degrees. It started at negative 30 degrees or negative pi over 6. That way, I was able to get this as well. Pew, pew. All right, so that gives me the area of the outer loop. Now, let's say that I start regaining myself and I spray the inner loop with water. Here's the inner loop. Okay, again, I've already come past here. Now I'm going to journey this way and then back out. The inner loop starts at 7 pi over 6. So again, let's say I continue to shoot the water. I'm like, choo, choo, choo. And I shoot up like this and back around. And again, the people rush in at me on this side because they're tired of getting hit. And finally, at 11 pi over 6, they overtake me and knock me down. So basically, that's why I have the limits of integration where I do. Now, by now, we're probably all exhausted. College Board's expectation typically is not to have you FOIL these out and put all those 11 pi over 6, 7 pi over 6, negative pi over 6s in. That's just too time-consuming. So at this point, we're going to let the calculator do the dirty work. You want to show your limits because that's obviously you showing that you have some knowledge. But from here, the grunt work should be done by the machine, not by the human. When you do all this work on the calculator, the area of the outer loop comes out to be 35.525046. And the area of the inner loop comes out to be 2.1740658. Obviously, we want the area between the loops, so we simply perform a subtraction. 35.525 minus 2.174 is going to give us our final answer, It's 33.35098. So again, College Board will accept either 33.350 or 33.351 square units. So that's the area between the loops.